In this particular video, we are going to look forward for two concepts of physics, which we already know, yet sometimes it becomes confusing. We know what is called mass and what is called weight, as they are used sometimes interchangeably, which is wrong. Now, if you consider a ball or any kind of an object and we call it how much amount of mass in it, you can talk or you can think that how much stuff is considered, how much stuff is inside this particular object, or you can say how much amount of atoms and molecules. So this would make up the stuff of the body of this particular object. Also, in other words, you can tell that how it reacts to force, how much it reacts to the force. So if you have a mass more, you will accelerate less. So for example, if I've got a mass m1 which is bigger, then the acceleration would be less. And if you have a mass m1, same m1 mass which has a less mass, the acceleration will be higher. So, and what is weight? This is mass, and now we talk about weight. So weight is basically the force of gravity on an object. Weight is the force of gravity on an object. So when we say that we have, say for example, this is an object which is right on the floor. So weight would be the how much force of gravity it is putting on the object. How much force of gravity it is putting on the object. So if you say that we have a mass of 70 kilograms, means I have a matter of 70 kilograms. So if we say that we have a mass of 70 kilograms, it means that we have a matter of 70 kilograms. You should tell that your weight is 70 kilogram. Weight is a force that the earth is pulling down, or the force of gravity on my mass. Now, considering this part, if we can take the Newton's formula, the basic formula, which I would be describing about the derivation in another video, Fg, that is this is the force which is equals to G, the universal gravitational constant, multiplied by first mass m1 followed by an m2 divided by r squared. So this is the gravitational constant, and these are the two masses, and this is the distance. This is the distance of the objects from the centers. So now what I'm trying to tell you is that this part, this G, m1 and m2, sometimes this entire part is considered to be, a small g. This is taken into as a small g. So we can write, and we know this is the gravitational of Earth, gravitational force of Earth, and we know it is approximately 9.8 meters per second square. So this would be the value. This would be the value of G. So the force of gravity something means that the surface on Earth is 9.8 meters per second square. Now if we consider this mass as 70 kilograms, this mass is 70 kilograms. So in that case, what we can take is that it would be 9.8 meters per second square, which is the value of this G multiplied by 70 kilograms. Now you might ask me a question that how far this is coming, this particular equation, how this is coming. This force, this part I have taken, I consider this part, say for example this one. If I take this, considered this G multiplied by this part. I'm not considering this for the time being, so this one. So this actually solves, and it gives you a value of roughly 686 newtons. It gives you a value of 686 newtons. Now this is something which we have discussed, or maybe we have not discussed earlier. This is a unit of measurement. So we can tell now this Newton, we can write it as N. 1 newtons equals to 1 kg meter squared. Right? So this is the value of 1 Newton. This is the value of 1 Newton. In other words, we can tell 1 Newton of force is the force required to accelerate an object with a mass of 1 kg 1 meter per second per second, that is squared. I mean to say 1 meter per second square. So if we take this part, say for example, this part, I am ignoring this equation. Say for example, I'm putting it in other way. We know from another equation that weight equals m times g. Simple. We take it as this part. W equals m multiplied by g. This is the mass, which is 70 kilograms. This is the gravitational force on Earth, which is 9.8 meters per second square, right? So even if we ignore this part and we take this equation, what we get is that we get W equals to 70 kilograms multiplied by 9.8 meters per second square, right? And it again gives the same value, which is 686 newtons. And if we convert from this part, which is 1 Newton, what we get is 69.95. We write it as kilogram force. We should not write it as kilogram because it is involved, it is kgf. So kilogram force. So what we have shown is that either from Newton's this formula or whether you consider W equals mg formula, what we are getting is that when we are getting a stuff that is a mass of 70 kilograms, its weight is 686 newtons, or it is 69.95 kilogram force. So in case that in our colloquial conversation we say that we have got a weight of 70 kilograms, it is wrong. Technically it is wrong. We should be considering the mass as 70 kilograms. Now, considering this part, I would also like to tell you another important thing, that is, in English system or an imperial system, we talk about pounds. We talk about pounds. So what, say for example, if I'm standing here, I'm very messy in my drawing. So if you're standing here and if I consider that my mass is 160 pounds, I consider at pounds, I write it in short form. This is my mass of 160 pounds. So does that carry any meaning to this system? Yes, it does. The unit of mass in imperial system is denoted by SLUG. Now this actually is the name of a snail which is generally found in the gardens, but this is just a general name. The SLUG is also the name of a snail which is found in the garden. So let us shift our concentration from botany to physics. So the unit of mass in imperial system is called SLUG. And I can tell you that 1 SLUG equals to 1 feet per second squared, right? So in case of getting an mg, which is meters per second square, we are getting the same thing as 1 feet per second square. So the force of Earth is also, we can call this 160 pounds as the force of Earth of gravity is 160 pounds. So how do we compute this part? So we get 160 pounds, I write it as LBS, which makes it short, and we divide both this part by 32 feet per second squared. This part is also 32 feet per second squared. This is 32 feet per second squared. So this gets cancelled out, and this we solve it as 5. So what we are getting over here is this one. We get is 5 pounds, and I change this and it goes up to there. So second square feet, right? So I just shifted this. Instead of writing it as 5 pounds, I flipped it over. So 5 pound square feet, right? And this is exactly equals to 5 slugs. 5 slugs. So if my mass is 70 kilograms, or I say for example, if my mass is 70 kilograms from here, my weight is 686 newtons, or my weight is 69.95 kilograms force. This is what we compute. But if my weight is 160 pounds, then my mass is 5 slugs. So if my mass is 70 kilogram, my weight is 686 newtons, or we can convert it in kilograms, which we found. But if my weight is 160 pounds and my mass is 5 slugs. So 1 slug of mass, I can write it in this way, that basically 1 slug of mass equals to 32.17 pounds, roughly pounds, right? So in case of G being 9.8 meters per second squared, right, what we get over here is that we get one slug, G equals 1 feet per second squared. So this is basically what we told you in the British Imperial system, how we can compute mass. So if my weight is 160, my mass will be around 5 slugs. Now we also know from this particular definition of mass and weight, what we can tell you is that mass never changes but weight changes. Mass never changes but weight changes. But how can we look into that? This is physics, so we need to find it out. So we take the basic formula again. We take W equals mg, right? Now we are considering three positions, three things. One is the Earth, one is the Moon, and another is Jupiter. And we are going to see that if we are standing here on Earth, this is the Earth we are standing upon, and if you move to Moon and Jupiter, does the mass going to be constant? Is it going to be same? So, and we take in both the cases my mass is 70 kilograms. Let us take the position of Earth. We know that by the formula of mg, we can write its mass as 70 multiplied by 9.8 meters per second square. This would be kilograms. And this roughly gives, as we have seen, 6.7 newtons roughly, and this comes to 69.5, so I'm rounding off to 70.2 kilograms. So my weight right at this moment with the computation of weight on Earth, it's come to around 69.5, so I take it as 70 kilograms mass. Now, if I go to Moon, I'm taking this considered to be Moon. Moon's gravitational force, that is the G. Now we are considering Moon. In case of Moon, Moon's gravitational force is 1.62 meter per second square, right? It is 1.62 meters per second square. So if we do with the same kind of a formula, W equals M multiplied by G, so what we get over is 70 multiplied by, again it is kilograms, it's 1.62 meters per second square, right? And what we get over here is that 11.56 kilograms. So my mass, which was 70, has come down, and I will weigh less in Moon. And that is why you see astronauts jumping around, because they are losing the weight. The weight is less. Now let us consider to be in case of a Jupiter. Now Jupiter's G, that is the gravitational force, is higher. It would be 24.79 meter per second squared. Again, we take the same formula, W equals mg, and what we get is 70 kilograms multiplied by 24.79 meters per second squared. I get 17353 newtons, which I convert would be 1769.51 kilograms. So if I am weighing 70 kilograms on Earth, it is going to increase huge, and it is going to be 1769 kilograms in Jupiter. So what we have shown rightly is that weight continually changes from Earth to Moon and to Jupiter, but the mass is always the same. So if our mass is 70, our mass is 70 and our is 70. But in case of Moon, it has come down. In case of Jupiter, it has gone up. You can take similar examples with Neptune on other planets, and it is a very simple computation. And with this kind of a computation, what we have understood. So let us just summarize in all what we have seen is that we have seen that mass means the general stuff which is considered within an object. It is atoms and molecules and all those stuff. Weight is defined, if I take this as weight, Weight is defined by this formula of W equals mg. This is a force of Earth on this particular object, or if we can even consider by this formula, and we can calculate the weight. And we have also seen that in the British Imperial system, mass is defined in terms of SLUG. So 70 pounds, we have seen how it will be in terms of SLUG. This particular G, which is the gravitational force of Earth, it would be 9.8 meters per second squared, which gradually changes in case of Moon, in case of Jupiter and others. SLUG, as we have considered, is not measured in terms of feet. It is measured in terms of feet. So it would be 1 SLUG is equals to 1 pound multiplied by second square by feet, which we have seen in this particular formula earlier part. We have seen that. So SLUG is basically measured in feet and G is measured in terms of meter per second square. So this is a particular calculation which have shown how mass remains constant and weight changes. Now, last and the most important part of this, if we can find out that in space, we haven't considered space. And in space, we know that G equals 0, right? So even if we put this formula W equals mg, so the mass, even it is 0, it is going to be 0, and my weight is going to be a big 0. And that is the reason you see that the astronauts float in space, because the G is 0. In Moon, it is so less that they keep on bumping and jumping in these videos you must have seen. In Jupiter, it is going to so high, I don't think they're going to be alive. We are going to crush down, these things are going to crush down, our bones are going to crush down, and we are going to die. So it shows that mass with 70 kg, how the weight changes in each and every planets and areas which are moving. Thank you for watching this video. Watch out more for physics.